Hi students, in this video we're going to talk about graphing polynomials in factored form. We're also going to talk a little bit about graph behavior and where some of our polynomial graph behaviors come from in regards to their equation. All right, to get into this we need to do some factoring reviewing just to make sure that we're on the right page. In this particular one we've got a cubic polynomial, and I see that all three of these pieces have some stuff in common. All of them are multiples of 2, and all of them have an x. So the first thing I'm going to do is to take a common factor out. That's a 2x. That would leave me with an x squared. So if I did 2x times x, I'd get 2x cubed. 2x times, well, that would be 6 and an x. And then 2x times a positive 5 gives me 10x. All right. Looking at the inside of this, by golly, that looks factorable. Our first term is just 1x squared, but I'm going to do this out kind of a slower way just to make sure that we're all on the same page. You may be able to do this very quickly without this, and that's okay too. I notice that if I multiply my a times c terms, I get 5x squared, and that my b term is going to be negative 6x. I'm going to try to break up my b term in a way that would multiply to 5x squared. And I also know since b is negative, the only way I can get a positive by multiplying is I have to have a negative number and a negative number. All right, two things that multiply to positive 5 and add up to negative 6. Well, 5 really only has two factors, 5 and 1, or negative 5 and negative 1. And those things add up to negative 6 if I make them negative. Each is going to get an x. And what this allows us to do is do factoring by grouping. So we got x squared minus 5x minus 1x plus 6. There's my minus 6x. I look at my first two terms. I can take an x out of both, leave me with x and x minus 5. My second two terms, I can take, sorry, I screwed up in writing this down. This should be a 5, not a 6. 5, not a 6. I can take a minus 1 out, and I can left with an x, and 5 divided by negative 1 is minus 5. Cool. So my factored terms here, x minus 5 and x minus 1. At this point, our polynomial is factored completely. What I'd like you to recall about graphing these things is that we factor because if this were a function is equal to this polynomial, this helps us to come up with a pretty good sketch of what's going on here. We need to identify our zeros. And to do that, we use something called the zero product property, that when we set this equation equal to 0, the only way that can be true is if one of these three pieces were equal to 0. So 2x equals 0 gives us 1, 0. At x equals 0. We get x minus 5 equals 0, which gives us a 0 at x equals 5. And we've got x minus 1 equals 0, which gives us a 0 at x equals 1. The other thing that we can talk about with regards to this is our end behavior. And in looking at my graph, the first thing I notice, looking at my equation, we have a positive leading coefficient. That tells me that my end behavior for this graph is going to go up and to the right. We have a positive graph. As we go to infinity, it's going to go up and to the right when we're talking about polynomials. Each of these three terms is what we call a single root. That means that our graph is going to pass through the x-axis at those places instead of bouncing off. We're going to see some double and triple roots as well, and we'll talk about those in a few minutes. So if I'm going up and to the right, if I want to pass through all these points, I've got to make a smooth curve that connects them. And I can only cross the x-axis at those places that I identified. That's really why we find the zeros, is that if we can't cross at any other place, if we know all of those pieces, that helps us a lot. The last thing that we really do for this is find the y-intercepts, and usually I'd find that before finding the end behavior. But in this case, since we have x equals 0 as a root, that also means that's a y-intercept. When x equals 0, y equals 0 as well. Okay, here's another version of the same problem. This one's already been factored for us, which is nice. I'm going to start identifying my zeros, so x equals 1. 2x plus 4 gives us x equals negative 2. X plus 5 is going to be x equals negative 5. X minus 3 is going to give us x equals 3. All right, I'm going to do my y-intercept next. We didn't really get to do the math for this one last time, but that's when x equals 0. So we've got 0 minus 1, 2 times 0 is 0 plus 4, 0 plus 5, and 0 minus 3. So we end up with 2060 as our y-intercept, which is here. I've got positive end behavior. None of my x's have negative coefficients, so we don't even have to worry about that. So we know my graph is going to go up and to the right. And none of these are double roots. That means that none of these are factors that look like this and have a squared term. That would say that would have a multiplicity of 2. If this were the case, where we cross the x-axis normally, we would bounce off instead. Double roots create bounces for us. In this case, we don't have any of those, so we're just going to pass through each time. I'm going to do a nice loop down, up through 60, back down, and in this case, we end up going up as we go to the left as well. Because we have 4 pieces here, this is what we call a polynomial of an even degree, and the end behavior of this would say that as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches infinity as well. In other words, as you go to the right, we're going up, and as you go to the left, we're also going up. All right, here we've got a couple of things that make this a little bit more complicated for us. The first is I have a bounce off my x-axis. That means that term has to be squared. If I've got an x equals 2, we're going to end up with x minus 2 to make that 0. And because it's a bounce, I'm going to square it. Going straight through at 7 is going to be x minus 7, but with just the power of 1. And because I don't know what my leading coefficient is, I'm just going to put an a there for a second and say that y is equal to a times the quantity x minus 2 squared times x minus 7. And the way that we find a is we use our y-intercept, which looks like it's at negative 14. We don't know what a is, and we'll leave that. For the y-intercept, it's going to be 0 minus 2 squared and 0 minus 7. So we get negative 14 is equal to a. Negative 2 squared is 4. And then we've got negative 7. So negative 28, that tells us that a is going to be a half. My equation is going to be 1/2 the quantity x minus 2 squared times the quantity of x minus 7. We're going to do the same thing here. And one of the things that I notice is that in this case, we've got 2 different bounces going on. So we're going to have an x plus 6 squared for my leftmost bounce. And that looks like an x minus 5 squared for my rightmost bounce. I'm going to put that a in front again. And now I'm going to try to solve for that. Here we've got 1200 is equal to a. If I plug 0 in for x, 6 squared, and then 0 in for x, negative 5 squared. So we got 1200 is equal to a, and 36 times 25 is going to be 100 times 9 is 900. Solving for a, we end up with 12 over 9 is equal to a. which is 4 over 3. That makes our final equation. Y is equal to 4/3 x plus 6 squared times x minus 5 squared. And for our next one, we've got a pass-through at x plus 8 is our factor for -8 being a root. I'm going to include include a coefficient there. And then we don't cross back through. When we don't cross back through, what this means is that we have some imaginary roots. It's really hard to predict what those values would be. However, when we have a graph that should have, in this case, 3 zeros, 3 x-intercepts, but we never come back down, graphically, that's what happens when we have imaginary roots. So in looking at the answer choices, I'm going to first cross out the ones that don't have an x plus 8. So that means that one and that one are gone. And then I've got to decide if x squared plus 16 equals 0 or x squared minus 16 equals 0 gives me imaginary roots. I'm going to look at the one on the right first because that's not going to be the correct one. That gives us x squared equals 16, which means that x is equal to plus or minus 4. Those are not imaginary roots, so those are not the ones that we're concerned with. If I try to do that on the right, we get x squared is -16. And if I take the square root of both sides, we get x is equal to the positive and negative version of, square root of -16. Oh, that's 4 and I. That's why this is the one that gives us what we want. This is the one that is possibly this graph that we're given. I'd also like you to notice that we're not shown the scale on the y-axis because we don't have that information to work with.